So let's cover a couple of quick facts about matrix inverses. So first off, a matrix can only have one inverse. So in other words, if A is invertible, then its inverse is unique. And the way to show that this is true is actually kind of a neat way of arguing. So let's look at it real quick. What we're going to do is we're going to suppose that there's two inverses. So suppose B and C are inverses of A. Then what we'll see is that secretly B and C are the same thing. So the way it works is that if we start with the product BAC, well, let's see, so I'll start with some nonsense here. BAC is equal to BAC. And on the one hand, we can put parentheses around these two, and on the other hand, we can put parentheses around these two. Now, since C is an inverse of A, I can write this as B times the identity, because if C is an inverse of A, then A times C is the identity. And then that tells me that this is just B. Meanwhile, if B is an inverse for A, then I know that B times A is the identity, and the identity times C is just C. And now if I read from left all the way to right, this equation says that B is equal to C. So if I have two inverses B and C, then secretly they were the same all along. And that's a proof. Okay, so next up, we have that a triangular matrix is invertible if and only if it has no zeros on the diagonal. And so this one I'm not going to prove right now. We'll come back and we'll talk about it after we've discussed determinants in Chapter 3, and we'll see that this is really easy to prove then, but it would be challenging now, so we'll just skip it for the moment. And then lastly, suppose that we have an invertible matrix. If A is symmetric, then A inverse is also symmetric. And just by parallel with the earlier results we talked about with symmetry, AA transpose and A transpose A will also be invertible. Okay, so let's see, for the first one there, when we're given something and this says A is symmetric, what you should think is the definition. And the definition is this equation right here. A transpose is equal to A. So, given that A transpose is equal to A, does it follow that A inverse transpose is equal to A inverse? Well, that should be your question. Okay, so let's see. So, and that question is exactly how we go about proving this thing. So, let's see. What I want to do is take the transpose, so I'll look at A inverse and transpose it and see what I get. Well, I just saw a theorem that said that A inverse transpose is A transpose inverse. So that was by the previous theorem that we looked at on the last video. And so then on the inside here, I say, oh, there's a copy of A transpose, and we're under the assumption that A is symmetric, so that means I can make this substitution anytime I like. So this is actually A inverse. All right. And then I look at this thing that I have here at the end, and it's A inverse. So reading from beginning to end, this says that if I take the transpose of A inverse, I get A inverse. So A inverse is symmetric. And that's a proof for that one. As for the other one, well, if we're given that A is invertible, then we know that A transpose is invertible by the theorem that we did in the last video clip, because we know that we have a formula for it. And then we also know that if we have two invertible matrices, then the product of two invertible matrices is invertible because we have a formula for it from the other part of the theorem that we did in the last video, which says that if you look at the inverse of a product, then it's going to be the product of the inverses in the opposite order. So AA transpose is invertible, and we are done.